Hi everyone, welcome to Drawing Hub. This is Sanjana, and in this video we'll be discussing about compiler design. So what is compiler? Okay, so here you can see a figure. Compiler. So here we have a compiler, then we have the source program, target program and error message. So we can understand from the figure that compiler is something that can convert a source program to a target program, and in this process of converting the source program to target program, if there are any error messages, that can be also sorted out. So what is compiler? Compiler is a program that can read a program in one language. So what will compiler do? First, it will read a program in one language, and that language is what we call the source language. And then it will translate this into an equivalent program in another language, and that is called the target language. And one of the important role of the compiler is to report any errors in the source program that it detects during the translation process. So this conversion is what we call the translation process. Then comes what is compilation. So this is the process of converting source program from one programming language to another. Okay, as I've told you, we will convert the source program to target program. So this process of conversion is called as translation or compilation. So compilation is a process of converting the source code into object code, and we do that with the help of the compiler. And compiler has two parts. What are the two parts? Spare me with this. Okay, I'm sorry about that. Okay, so compiler have two parts. One is the analysis part. Okay, the first one is the analysis part, and the second one is the synthesis part. Okay, so we have the analysis part and the synthesis part. Again, this analysis part is divided into three. Okay, here we have lexical analysis. Okay, we have lexical analysis, we have syntax analysis, we have semantic analysis, and in between this we have another phase which we call as the intermediate code generator. And in synthesis we have two parts, which we first one is code optimizer and the second one is code generator. Okay, code optimizer and code generator. So these are the six parts that we have in the compiler phases. So these are, when the question is asked, we have to write about all these six phases: the lexical analysis phase, the syntax analysis phase, the semantic analysis phase. Then we have an intermediate code generator, and in the synthesis phase we have the code optimizer and then the code generator. Okay, so the compilation has two parts: analysis and synthesis. And in analysis it have three phases: lexical analysis, syntax analysis and semantic analysis. And then we have the intermediate code generation. And in the synthesis part we have two phases: code optimization and code generator. So this is the figure. That is, we have analysis phase which is in the front end and the synthesis phase which is in the back end. Okay, so in the analysis phase, what will happen? The source code will be put to analysis phase. And the analysis phase will give us an intermediate code representation. We will get an intermediate code representation. So from this intermediate code representation, it will be fed to synthesis phase. Synthesis phase in the back end. So from here, the synthesis phase will give us the machine code. So this figure is also important. Now these are the phases of a compiler, as I've mentioned. We have the source code which is moved to the lexical analyzer, then to syntax analyzer, semantic analyzer, intermediate code generator, optimizer, code generator, and finally we get the target code. So in this process, for all the six phases, it will be mapped to the symbol table as well as the error handler. So now we will learn each of the phases one by one. First one, we have the lexical analysis. So this lexical analysis, as we know, it is the first phase of the compiler. Lexical analysis is the first phase of compiler, and we also called it as a linear analysis or scanning. So in lexical analysis, a scanning process is done. So this it goes in a linear fashion, and for that reason lexical analysis is also called as linear analysis or scanning. The lexical analysis phase reads the characters in the source program. So what does this lexical analysis phase do? So as I told you, it is about scanning. So it will read the character in the source program. The lexical analysis will read the characters and then it will be grouped into tokens. So what are these tokens? They are a sequence of characters which will have a collective meaning. And then we have a common form to write the output. That is, for each lexeme, the lexical, and we call it lexeme. Okay. So for each lexeme, the lexical analyzer will produce an output token. We'll have a token that will be in the form token name attribute value, in this form, token name attribute value. Okay. So we have an example. I am having a equation, position equal to initial plus rate into 60. So how can I write that? Okay. I have, okay, suppose position equal to rate, oh sorry, initial position is equal to initial plus rate into 60. So how can we write it? That is, a lexical analysis is reading it. Okay, it is scanning it. So how can we write it in that context? What will we do? So position, it is a value. So we can tell that is an identifier. So position, we know position is an identifier. Okay, position is an identifier. So how much? What is a position? This is the first identifier we have identified. So I can write identifier ID. It's short form for identifier ID 1, because that is the first position. Okay, that is the first identifier I have identified. And then I will use these greater than, lesser than symbols. Next, what is the next one? I have the assignment symbol equal to. Okay, so that is not an identifier. So how can I write? I can write equal to. Then again, I found another identifier, that is the initial. So this is the second time we are finding an identifier. So how can I write? I can write, okay, this is also an identifier, but this is the second identifier we have found. So ID2. And again, we have a plus operator, right? So that will be plus. We can write everything will be in greater than, lesser than symbol. Again, I found another identifier. So how will we write this one? Okay, this is also ID, and what number will it have? It will have 3. And then again, I found another operator, that is into, right? Multiplication symbol. And then 60 is a value. It is not an identifier, it is not an operator. So it is a value. So I will just represent it here like this. So all this is in one single. So this is how we represent a lexical analysis. We are scanning it from left. See, from where did we start? We started from left and we moved to the towards right, right? So from starting from left to right, we have scanned the elements, and that's how it works. Okay, so here this is the explanation. Position. So here we have position. This is a lexeme that would be mapped into a token. So the position is the lexeme, and then I want to make a map it into a token. And here ID is an abstract symbol. For identifier, I have written it in a short form ID. And then 1, I have written 1. Why? That is, it is a first entry in the symbol table. The position of the ID is the first one. It points first one. That is why I have written ID, 1. And the symbol table entry for an identifier holds information about the identifier. So in symbol table, it will have informations about the identifier, such as its name and type. Then we have assignment symbol. Assignment symbol, that is equal to. So this is also a lexeme, and then we have mapped into the token equal to. And now since this token needs no attribute value, we don't want the, see, it does not have any attribute value, so I don't have to put any 2, 3. I don't have to put any values like that. Okay. And then again, initial, that is an also an identifier. So how will I write? I will write ID2. Then plus is again a, it is a lexeme which I can write. It's an operator, so I can just write it plus in the greater than equal to symbol. Then again, rate is an identifier, and then a multiplication symbol is also mapped into token. And finally, 60 is also a lexeme. So this is how we get at last. So this is the lexical analysis phase, how we write it. I hope you've understood what is lexical analysis. So that is the first phase. Now moving on to the second phase, we have syntax analysis. So syntax analysis, I can also call it as a hierarchical analysis or parsing. Okay, so because in syntax analysis, it is moving in a hierarchical format. That is why I can call it as a hierarchical analysis or parsing. Okay, so here we have already grouped the token. So now here we will do, what will we do? We'll group the tokens of the source program into more grammatical phrases so that the compilers, see, we need to synthesize the compiler to get the output, right? So for that purpose, we are grouping the tokens of the source program into grammatical phrases. And this we do with the help of a syntax tree. See, from the word syntax analysis, syntax tree, we use syntax tree. So then what is a syntax tree? A syntax tree, it is a tree which is generated as a result of syntax analysis. Here, the interior node, we have a tree. Okay, so here in this tree, the interior nodes will be operators and the exterior nodes are the operands. Okay, so how will we get it? So here we have id1 equal to plus and all. Okay, so I want to create a syntax tree. Okay, I have equal to symbol. Okay, the assignment symbol, and then I am mapping it to, okay, and I have to give it to id1. So id1, it came in the left hand side. Okay, id1. Okay, so because it comes here, and rest everything in the right hand side of equal to, everything will come on the right side, right? So whatever, and also remember we have the operators in the interior and operands are in the exterior nodes. See, operators are in the interior nodes and in the exterior nodes we have the operand. So we have to keep those two things in the mind now. Okay, and then we have the plus symbol. Okay, plus symbol comes next. So plus symbol is between what all? I have id2. I have id2 and then the rest of it. Okay, I have id2. Okay, id2 and then the this thing, that is id3 star 60 is there. Okay, so again I have to go with star. Why? Because everything else comes after plus, right? So star means that is between id3 and 60. Okay, then I've mapped it. Okay, so this is how the whole thing is. So let's see if this is similar to what we have. Say we have equal to, look here, equal to, in the left hand side we have id1 and the rest, this whole thing comes, where does it come? It comes on the right hand side. Then again we are moving, again we have to remember about the operator and operand thing. Okay, operators should be in the interior nodes. Okay, so we have here plus y, and then plus means id2 should come in the left hand side and rest everything should be in the right hand side. So id2 is in the left hand side and rest everything is in the right hand side. Then again we are looking, we have star. Okay, after that star means id3 into 60, id3 into 60. Okay, so that we have completed drawing the syntax tree. So that is it about syntax analysis. So we have completed two phases. We have completed lexical analysis phase and also we have completed syntax analysis phase. Then we have the semantic analysis phase. Semantic analysis phase. So in this phase, we'll check the source program for semantic errors and it will gather any type information, because after that we have a for the subsequent code generation phase. So for that purpose, any type information is there. That is what the semantic analysis will look for. And if there is any semantic errors, an important component of semantic analysis is type checking. So here what does the compiler does is that it will check that if each operator has matching operands. So if does not have a matching operand, that is if each operator does not have a matching operand, then means that it is semantically incorrect. So that is called type checking. Checking whether the operators have matching operands is what we call as type checking. The semantic analyzer uses the syntax tree. So what is the input for the semantic analyzer? The syntax tree is the input for semantic analyzer. And also we use the information in the symbol table. So we use the syntax tree for input. Also we take the input from the symbol table. To check the source program for semantic consistency, with the language definition. Now it also gathers type information and save it in either. So either we will save those information we have gathered in the syntax tree or the symbol table. That is because our next step after semantic analysis is intermediate code generation. So for that, we need to collect the information. We need to gather the type information. After gathering, we can store it in the syntax tree or the symbol table. That is semantic analysis. So how does it happen here? We are just designing the floating point number. So okay, here we have the operator. So in this case, we are looking for float. Okay, everything is float. So I'm giving here float. So all this will be float. We have all this as float. Okay. And now even coming to 60 over here, we have to write something. We have to insert another box called into float. Okay, this is in an integer format, right? So I need to write into float. Into float. I'll put it in a box. I'll move it over here. Okay, so this is an extra thing that I have to add in semantic analysis. See, it is similar. Everything is same. We just copy everything from syntax tree, except for we are adding the float values over here. So because position, initial and rate have been declared to be floating point numbers. So they all are floating point numbers, and this is 60 is an integer alone. That is why int means integer. So I'm converting the integer to float type. So the semantic analyzer discovers that the operator star, I have here operator star. So this one is applied to a floating point number rate and an integer 60. So here all the integers is converted into floating point number. It is in this case, okay, not every time. And also in this figure, we have the output of the semantic analyzer has an extra node for the operator. See here, we have an extra node for the operator into float. So that explicitly converts the integer argument into a floating point number. So this is the proper figure for it. Then comes our next phase. Okay, so we are done with the first part, that is analysis part. We have learned what lexical analysis, what syntax analysis, and what semantic analysis. And now we have the intermediate code generator. So front end is over. Now we have the intermediate code generator. So in the process of translating a source program into target code, so while translating a source program to target code, a compiler may construct one or more intermediate representations. So these representations can be of any form like syntax tree or anything. So there will be many intermediate representations and can have a variety of forms. So syntax tree, as I have told you, is one form of intermediate representation, and it is the syntax tree is usually used commonly in syntax and semantic analysis. Both of these places we are using it, right? And after the syntax and semantic analysis of the source program, many compilers will generate an explicit low-level or machine-like intermediate representation. And that is what we can think of as a program for an abstract machine. So this should be simple and easy to produce, and it should be easy to translate into target machine. This intermediate code generator, whatever code, intermediate code we are getting, that should be simple, it should be easy to produce, and it should be easy to translate. We should be able to translate it into target machine easily. That is about code generator, intermediate code generator. So again, we are looking, we have position equal to initial plus rate into 60. So this was our first problem, right? We have position, as of now I'm writing it short, okay? Position equal to initial plus rate into 60. Okay, I have position plus rate into 60, and now I am taking a value. I'm taking a random value t1. Okay, I'm taking a variable t1, and inside this t1, so we are looking at with reference to the semantic analysis. See, I'm looking at with reference to this one. Okay, so in t1 I am storing this into float 60. Okay, into float 60. So I can write like this: t1 is equal to into float 60. So I have stored both of these into a single place. Okay, and in, okay, then I have another variable t2. Again, I'm looking at the tree. Okay, this part is over. Then I can say id3, id3 into float 60. I can write like that, right? So what does that mean? T1. T1 is into float 60. So I can write into T1. What is into T1? ID3 into T1. Okay, so ID3. See? ID3 into T1. ID3 into T1. Why? Because T1 I have already stored into float 60 value into T1, right? So I don't have to repeat it again and again. So ID3 into T1, I have stored that. Then what is the next thing? Again, I need to get another variable T3. Okay, I have another variable T3. Okay, what do we do with this? T3, I have ID2 plus this whole thing. So this whole thing is what is it? T2. So ID2 plus T2. I can write ID2 plus T2. Okay, ID2 plus T2. Is that right? Yes. Again, then what do I do? Okay, so ID2 plus T2. So this much value we have. Whole left hand side. Whatever is there in the right hand side, I have all those things. Now, only the left hand side. What is left hand side? ID1. I need to assign it to ID1. So I don't have to bring in another variable for that. I can just use ID1. And ID1 is equal. You can write ID comma 1 or ID1. Okay, so ID1. ID1, how do we write? So I have T3, right? T3 consists of this whole thing. So ID1, I'm just assigning the value of T3 to ID1. This is intermediate code representation. So this is using a 3 address code. So it have a sequence of assembly like instructions with 3 operands per instruction. Okay, that is about intermediate code generator. And now we are moving on to our synthesis phase. So in the synthesis phase, our first phase, what do we have? It is code optimization. So what all did we finish so far? We learned about lexical analyzer, we learned about syntax analyzer, about semantic analyzer, intermediate code generator, and now we are moving to the synthesis part. And in the synthesis part, we have the first phase, code optimization. What is optimization? To make something better. So here, the machine independent code optimization phase attempts to improve. So here we already have an intermediate code. So I need to improve this intermediate code so that I will the target code that I get will have a better result. Okay, and the objectives for performing optimization, so faster execution. Why do I need to make the code more optimized? Because I want faster execution, and then the code, line of code, I want it to be shorter, or maybe the target code consumes less power. For all those reasons, I want to make my intermediate code much more optimized. So here, how do we make it more optimized? Look, okay, I'm not writing out there. So T1, as I know, T1 is into float 60. I have assigned that value. Okay. And T2 is ID3 into T1. Okay. So what is here? T1 first I assigned the value. Then in T2 I am calling that value. So instead of doing that, I can write T1. Okay. I have a variable T1. And then ID3 into, instead of taking it as an integer, I can write it in the float format. So directly here, this whole one step, I'm avoiding this step and I'm directly writing it over here. And again, so I have ID 3 into 60. Now this much is my first step. Then I have ID 1, and inside ID 1 I have ID 2, and ID 3 into 60 is already T1. I have already assigned it over there. So ID 1 is equal to ID 2 plus T1. The step is over. So I have made my code more optimized, more better. I have improved the result. Okay, and then I have the code generation. So our next phase is also over. Code optimization phase is also over. So we have studied about lexical analysis, syntax analysis, semantic analysis, intermediate code generator, and code optimization. Now the last phase is code generation. So how do we do this code generator? So here code generator will take the input of intermediate representation and not the code optimization phase. Okay, we take the input from the intermediate representation of the source program, and then we will map it into the target language. So the target language, how can we write? Okay, we can see that with respect to this one. Okay, so first one, t1 into float 60, that is the first step. Okay, so what do I have to do? I have a register. Okay, I'm having a register r2, and I have to load this id3. I'm loading id3 into r2. I'm loading it into the register 2. Okay, then I want to multiply whatever is there in r2. What is there in the register 2? id3 is there in register 2. So along with that, I want to multiply this 60. It's a constant, right? So I want to multiply r2 with 60. So that is done. Okay, now whatever I have in r2, I'm keeping it aside. Next, again, I have another id2. I have another id2. Or you can even check with this. Okay, so whatever I have in id2, I'm storing it in another register r1. I'm storing it in another register r1. So I'm loading it. Okay, it's not storing, I'm loading it. Then what do I have to do? I have to add this. id2 means it is now in r1. Okay, so I'm adding r1 and r2, and by default it is stored in r1. So here what will happen? It is now in r1, right? Whatever is, I have added r1 and r2, and the value is stored in r1. And now I want to assign whatever is there in register 1. I want to assign it in id 1. So so this is f, means this load f, mul f, this all stands because it is in floating format. Okay, so here again I'm having store f. So whatever is there in r1, I'm storing it in id 1. Okay, so finally the value in register r1 is stored into the address of id 1, so that the code correctly implements the assignment statement. So this is for that one question, our position equal to initial plus rate into 60. So the first step, the lexical analyzer, we have the syntax analyzer, the semantic analyzer, the intermediate code generator, the code optimizer, and the code generator. So this much step you have to do. And if this is for a 10-mark question about the 6 phases of a compiler, you also have to include about the simple table. Okay, now what is a simple table? Again, a simple table, it is a data structure, and inside this data structure it will have a record for each variable name with fields for, we have already discussed. Okay, so inside that we'll have the variable name, also the attributes of the name, and the data structure should be designed to allow the compiler to find the record for each name quickly and to store or retrieve data from that record quickly. So that is about simple table. And also have an error and reporting. So you have to also mention about this if it is coming for a 10-mark question. So error detection and reporting. So each phase can encounter errors, right? So after detecting an error, a phase must somehow deal with that error. So only then, only if the phase deals with that error, the compilation can proceed, so allowing further errors in the source program to be detected. So that is about error detection and reporting. Okay, that's it for today. Thank you.